Hi Lizzie, Mrs. Genoways here, and what more fun could you ask for on spring break than to sit and watch 80 slides of physics? We're just going to run through the Unit 4 notes. Some of it you were here for, some of it you weren't. So some I'll just zip through, and then some I'll actually work out the problems. So I don't know how long this video is going to be, so I may have to break it into chunks. We will just play it by ear. So here we go. So we've talked about vectors and scalars quite a bit. The only difference is now we're actually going to draw vectors, and we will do it by drawing an arrow. And as we draw these, arrows have a tip, and arrows have a tail. And we're going to refer to that later. And the main thing is that you realize that vectors are magnitude and direction, and magnitude is the word that messes everyone up. It simply means size. So scalar is magnitude only, but no direction. And we're going to look at the next couple slides that are going to really clear this up for you. So if you take a look at these 5 items, decide if they're vector or scalar. So you probably want to pause the video, think it over. So acceleration is a vector. It's the change in velocity, and velocity is a vector. Number of people on the plane is just a scalar. It's just telling us how much, how many. Duration of the flight, scalar. Displacement is a very important term. This is a vector. It does require direction. How far are you from where you started? So it is a vector. And amount of fuel is a scalar. It's just how much. Just like in math, there are certain terms you use when you add, subtract, multiply, and divide. When we're dealing with vectors, when we take 2 vectors and put them together, the answer that we get is called the resultant. Now there's really 3 ways that vectors can be put together. They could be going in the same direction, and to get this answer you simply add them. They could be going opposite of each other, and this you would subtract them, and then we'll look at the more complicated scenario where they're at angles to each other. So question 2, what is the resultant velocity of a plane flying 100 kilometers per hour south and a 25 kilometer per hour wind that is blowing south? Because those are both south, you simply add, and we get 125 kilometers per hour south. A vector has to have magnitude and direction, and we're always going to put in a unit. Looking at question 3, same scenario, only this time the plane is flying south into a north wind. Opposite directions, we simply subtract. 75 kilometers per hour south. Right, here's an example where we have 3 vectors. We have, in the easterly direction, we have 8 kilometers, and then in the westerly direction, we have 3 kilometers, and then in east direction, we have 12 kilometers. If we look at the first question, distance is a scalar. It simply wants to know how far has he gone. So we add 8 and 12 and 3, and we don't care about direction, 23 kilometers. But for displacement, direction does matter. So we have 20 kilometers east, 3 kilometers west. Opposite directions we subtract, and we end up with 17 kilometers east. Next, we're going to deal with vectors that are at angles to each other, and we're going to start with just right triangles. So what we're going to do is we're going to sketch the 2 vectors using what's called the tip-to-tail method. So we have the tail of the vector and the tip of the vector, and then we're going to use the Pythagorean theorem to find the third side. So if we had a vector that was going maybe 10 meters north, we would start drawing with our tip, go up with our tail, and if our next vector, let's say, was 6 meters to the east, we would put the tip on the tail of the second vector, and then our resultant goes from the beginning to where we ended up. And this will be the side that we are going to be looking for. So to solve for that third side, we're going to use Pythagorean theorem. Normally you think of that as a squared plus b squared equals c squared, but in physics I like to think of it as x squared plus y squared equals the resultant squared, because this line lies on the x-axis if we're thinking of a graphing coordinate system, and this line would lie upon the y-axis. And then we're going to solve for our angle, which is our direction, by using inverse tan. So second tan on your calculator, and it will always be y over x. And the only thing you have to remember is your calculator must be in degrees. So if you're using your graphing calculator, you can just hit the mode button, and it should tell you if you're in degrees or radians, and we have to be in degrees. And before we start solving problems, we have to think about what to do if our angle is pointing in a direction other than quadrant number 1. So just a quick review of the quadrant numbers, 1, 2, 3, and 4. And as you work through these problems, and we draw our resultant triangles, you will see what happens when your vector is in a different direction. So if your resultant ends up in quadrant 2, we subtract it from 180. Quadrant 3, we add our angle to 180. And quadrant 4, we subtract it from 360. So this would be something to maybe stick on a note card, because you will refer to this quite a bit. Okay, so my suggestion, whenever you're drawing a vector problem, is start with a dot. And this is going to be your starting point. You won't be able to forget where that is at. And the order that you work with vectors does not matter. Typically, I just do them in the order they're given. So a plane flies east at 90 kilometers per hour. And my next vector comes off of the tip, go north at 50. I also try to draw them semi to scale, so my 50 is shorter than the 90. Here's my resultant, which I tend to draw as a dotted line. And here is my axis, which helps me see that this vector is going to be in quadrant 1. So what I'm going to do is Pythagorean theorem. And then I'm going to solve for the angle using inverse tan. And it will always be the y over the x, so it will be 50 over 90. And then you can check your answer right up here to make sure that we're both getting the same one. Okay, this next problem will show what to do if your vector is in a quadrant other than quadrant 1. So we're going to start with our dot to show our starting point. We're going to go 100 kilometers per hour south and 25 kilometers per hour west. Here's our resultant. We're going to end up in quadrant 3. So first we'll do Pythagorean theorem. And solve for that. And then you will do inverse tan, y over x, 100 over 25. And when you get that answer, it comes out to be about 76 degrees. But because we're in quadrant 3, our rules say you have to add 180 to that answer. So our final answer will be 103 kilometers per hour at 256 degrees, not 76. Okay, question 7. We have a pyramid that is 136 meters high. And we know the total width, underlined for a reason, is 230. So to turn that into a right triangle, we're going to cut the 230 in half. So our base will be 115. And then we can simply do the Pythagorean theorem. And because we have no idea which direction this person is climbing, we're going to solve for the angle and just leave it as if it's in quadrant 1. But it will be y over x. And that is about 50 degrees. All right, here's another problem where we are going south for 40, west for 15, and north for 20. So we have to get our vectors that are similar, the north and the south, they're opposite. So we're going to put those together, and when we put them together, we end up with 20 south. Then you will draw that. So if I go 15 west and 20 south, You're going to do Pythagorean theorem and inverse tan, and hopefully you end up with 25 meters at 233 degrees. Remember, this is in quadrant 3. All right, which of the following are true? The first one is definitely true. Vectors must have a direction. Number 2, no. Scalars do not have direction. Number 3, also a no. You can add together both. And the last one is true. So 1 and 4 are your truths. All right, take a look at this one and decide which of the following are vectors, not distance, but displacement is, not speed, but velocity in any way, shape, or form is. And because acceleration is the change in velocity, it is also a vector. Which statement represents a vector? Anything that has magnitude and direction. So the first one is, the second one is, it is an acceleration. Number 3, also a vector, not 16 years old, not 60 minutes. Meters per second, yes, and in south, definitely yes. Meters per second squared, yes, and not temperature. So question 12 is giving you 2 vectors. We have a 6 and an 8, and the range of any vector measurement will be the answer you get when you add them and the answer you get when you subtract them. So in this case, it's going to be somewhere between 2 and 14. Okay, our next little section deals with what are called boat and river problems. And boat and river problems are always a 3-part problem. It is always done in this exact order, although sometimes I only ask for 2 of the 3 parts, but you must do 3. Part 1 is simply asking to solve for the resultant velocity. So the boat is traveling 4 meters per second east, and a current who's going 3 meters per second north. And you solve for the third side with Pythagorean theorem, and you solve for the angle with inverse tan. Go ahead and give that a try and see if you get 5 meters per second at 37 degrees. Part 2 of boat and river will ask for time. So on this problem, we have 2 banks of the river, and it's telling us that from bank to bank is 80 meters, and that is a distance. We're looking for how long does it take to travel shore to shore, so we're looking for time. We're going to go back to the very beginning of physics, where we had our velocity, distance, time triangle, and we are looking for the t, so we're going to take our distance divided by the velocity. But the problem here is we're not sure which velocity to use. The velocity that you use will always be the velocity that is going in the same direction as your distance. You will never use the velocity that you solved for in part 1, even though you did all that work to get it. So in this case, we're going to use the 4, and we get a time of 20 seconds. All right, last part of boat and river. We just solved for a time of 20 seconds. This one is going to ask you, how far downstream or upstream is the boat when it reaches the opposite shore? So as you rowed across the river, you thought you would end up in this spot, but really you ended up here at this square. So we're looking for this distance. Again, you have to use the same rule as we used on the previous problem. You must use the velocity that's in the same direction as your distance. Using your v/dt triangle, this time we're looking for d, so we're going to take our velocity, which is 3, times our time, which is 20, to get 60 meters. And here's a boat and river problem that you can try. Remember to draw your vector diagram tip to tail for your resultant velocity, and that's where you're going to have magnitude and direction, and then solve for time, and then solve for your distance.